virtually everyone can agree that pollution of all sorts is a huge problem. Whether it's the foul stuff in the air or the loud noise in our environment, it's clear that something has to be done to lessen the impact of pollution in our lives. I'm Jennifer Pulley, and today on NASA 360 we'll find out how NASA researchers are working to decrease pollution through a revolutionary program called ERA, or the Environmentally Responsible Aviation Program. Without a doubt, right? Pollution, it's a big problem. Well, surprisingly, it's one that humans have been dealing with for quite a while. If you look back throughout history, some of the first examples of pollution can be found in the form of soot on ceilings of prehistoric caves. This soot showed that our ancestors were living with high levels of contaminants due to inadequate ventilation from the open fires within their living space. But this wasn't the only way that our ancestors were exposed. Later in history, air pollution outside of the home increased tremendously when humans began forging metals. In fact, core sample research from the glaciers in Greenland indicates increased air pollution associated with Greek, Roman, and Chinese metal production. But the explosion of pollution really happened around the time of the Industrial Revolution. With the advent of industrialization, poor air quality began becoming a worldwide phenomenon. The emergence of great factories and consumption of immense quantities of coal and other fossil fuels gave rise to unprecedented air pollution. In fact, as early as 1881, American cities were enacting clean air laws around the country. Today, we have a much better understanding of pollution and its impact. So, what are we doing to minimize it in our lives? Well, there are hosts of private companies and government agencies that have made tremendous progress on our pollution problem. And one of the best examples of this is NASA's Environmentally Responsible Aviation Program. The goal of ERA is to conduct research into technologies and aircraft systems that will allow aircraft to simultaneously reduce noise levels by about 42 decibels, reduce emissions by 75%, and reduce fuel consumption by 40% over the coming years. If you think this is a big challenge, you're right. At any given time here in the U.S., there are about 4,500 airplanes in the air. 40 of the top 50 airports don't meet air quality standards, and commercial and defense aircraft emit about 250 million tons of carbon dioxide into the air yearly. And of course, one of the biggest challenges associated with making real transformation is that you can't shut down the airline industry while you make changes. The changes have to be added in gradually. Okay, right, there's lots of changes happening to decrease pollution. And one of the least talked about is how we plan to decrease noise pollution. Well, here at the Structural Acoustics Lab at NASA Langley, researchers are looking at aeroacoustical and structural acoustical changes within aircraft in the hopes of bringing down the decibel level, not only inside the aircraft, but on the ground as well. To find out how these changes are studied, I first spoke with Ran Cabell here in the Noise Lab. So, Ran, explain to us the difference between structural acoustics and aeroacoustics.
Well, aeroacoustics involves a study of sources outside the airplane. So things that make noise like propellers and jet engines, and then what you can do to make those things quieter. Now in structural acoustics, we're interested in how the noise outside the airplane gets inside the airplane. And so that typically involves a noise traveling through the structure, hence the name structural acoustics. So a big part of structural acoustics is sound transmission through structures. This room is where we measure sound transmission through structures. So we take a piece of the side of an airplane, for example, put it in this window, we excite it with sound on one side, and we measure the sound that comes through to the other side. Then we take those results, and we can go back to our computers and determine if we're going to have a noise problem inside an airplane or a helicopter, for example. And if we have a noise problem, then we can try to change the structure, or we can try to add treatments like insulation, fiberglass, for example, to try to make it quieter for the passengers and pilots inside the airplane.
Okay, so two distinct rooms. And this room I notice is echoing. That room over there looks like, it looks like a sound room.
That's right.
So describe to me how these rooms work.
This is called a reverberant room, which, as you noticed, means reflecting. So, and that room is the anechoic room, which means no reflections. So what we do is we create a lot of sound in this room. And if you look around, you'll notice we have about 24 speakers hanging on the walls and ceilings. And these are just like the speakers that you would have at home. And so we create a sound field in here, but there are a few unique things about this room.
Doesn't look like normal rooms.
That's right. If you look at the walls and the ceilings, they're not straight. They're actually kind of wavy. What we want to do is get a nice uniform level of sound in this room. So actually the wavy walls and wavy ceiling help us get a uniform level. So it's not extra loud in one spot or extra quiet in another. It's nice and uniform.
That seems interesting. You would think a flat surface would provide uniform. I would think that. That's interesting. It's the opposite.
Right. Actually, the wavy helps us get it nice and level. Another thing is we want to keep all the sound inside the room. We don't want it leaking out. So the walls are actually very thick concrete, about 3 feet thick. We also have 2 very large doors to close the room. So when we're doing a test, we close these massive doors to keep all the sound in. And another thing, very subtle, as you walked in the room, there's a gap between this room and the rest of the building. This room actually isn't connected to the rest of the building. It sits on very large springs in the basement. And again, the idea is we want to keep all the sound in this room. We don't want the sound going out through the floor or out through the walls. It's just filling up this room with sound. So once we've filled this room up with sound, we have our piece of the airplane fuselage or helicopter fuselage or even rocket in this window. And so it's getting bombarded with sound. Then we have microphones, and you can see the microphones through the window on the other side. And that's how we measure how much sound gets through that particular piece of the airplane or helicopter.
Okay, and you said the sounds in here. What sounds are you blasting through the speakers? Are you engine noise? What kind of sounds are you talking about?
We usually use what's called white noise. And you might say to yourself, that doesn't sound like a propeller or a jet engine. But white noise is a very generic kind of noise. So once we know how the structure responds to white noise, it's easy for us to take those results and then go back to the computer and say, okay, now let's apply a propeller noise or let's apply a jet engine noise, and we can understand how the structure would respond to that kind of noise.
It's kind of like a baseline, if you will.
Right.
How would I experience decibels just in everyday life of sound, those levels of loudness? Give me some examples.
A typical conversation would be about 60 to 65 decibels. I believe once it gets up to about 85 or 90, you'd start thinking it's getting kind of loud. If you're at a rock concert pretty close to the speakers, it might be 110 to 120 dB.
And we're talking maybe some ear damage.
Exactly. Very loud enough to damage your hearing. As you get above that, you're just talking more damage to your hearing and pain as well.
We've been talking about noise pollution and what a problem it is. Why is it so important for NASA to be testing this?
Well, a critical constraint in making it quiet for passengers and pilots is that the airplane has to be light enough to get off the ground. So we know we can make an airplane quieter by putting heavy objects on it, putting heavy insulation, heavy fabrics, things like that. But we need to do it without adding much weight. So that's where the challenge comes in and where NASA looks at advanced technologies. And what can we do maybe to redesign the structure to make it quiet in the first place? So that way we're not adding any weight, we're just making it so the structure doesn't let the sound through to the passengers. And another way, another technology we look at is called active control, where we would actually try to cancel the vibration of the structure and that way reduce the sound getting to the passengers.
Because if it doesn't vibrate, it's not going to create sound waves to get into our ears.
That's right.
Rand, thank you so much. We appreciate it.
You're welcome.
Stay tuned. You're watching NASA 360. Okay, so Rand just showed us some ways that NASA is testing the reduction of noise inside aircraft. And for those of us who fly often, that's great news. We also know that aircraft noise affects lots of people on the ground. And with air traffic expected to double in the coming years, we need to find ways to decrease the noise around airports and over homes. My friend Florence can tell us more about what's being done on that front. Hey, Florence.
Hi, how are you?
I'm good. How are you?
Very good, thank you.
Now, I would assume that engine noise is really the major concern when it comes to noise on the ground.
You're correct, and actually that is true only during aircraft takeoff, when the engines are at full throttle. But actually, during landing, the engines are near idle condition, and then in that case, airframe noise becomes a dominant noise source. So if you want to reduce the noise on the ground, you need to reduce both engine noise and airframe noise.
Talk to me about airframe noise. What do you mean by that?
Yes, airframe noise is a noise that is generated with the interaction between the airflow and the airplane fuselage, the wings, the landing gears, the high lift system. And so the noise resulting from that interaction is called airframe noise.
So how is NASA or working towards decreasing airframe noise and engine noise?
Okay, well, to decrease first airframe noise, the main components of airframe noise are the landing gears and the high lift system. If you look out the window and look at the wing, you see the flaps that are deployed at the trailing edge of the wing, as well as the slat at the leading edge of the wing. So those deployed surfaces are the high lift system. And all of the edges and gaps along those surfaces generate a lot of noise. So one way to alleviate this type of airframe noise, for example, this is what a typical landing gear looks like. Only this is a 6% scale model of the real thing. But you can see there is a lot of components. So it's easy to imagine that when the turbulent air is flowing through this, it's going to make a lot of noise. So we're looking at ways to change the geometry, the number and the layout of those different components so that it will result into less noise. For the high lift system, for example, for a flap, here you're looking at a section of a wing, and this is a flap that deploys when you're going to land or when you're taking off. And you can see that there is a side edge here, and the pressured air that is under the wing to lift the aircraft rolls here and forms a strong vortex right there at that edge. And the impingements of that vortex with that side edge generate really loud noise. So really, we want to eliminate edges.
How do you do that?
Well, it's very challenging structurally because acoustically we verified that it works really well if you eliminate that side edge and instead you fare in that side edge into the main wing. So it works great acoustically, but now it is a challenge structurally because this thing needs to be able to retract during cruise.
Okay, so we see this challenge with the airframe components. What about engine noise? I mean, how do you really reduce the noise? They're loud.
Yes, it is very loud, and there is two components to engine noise really. We're trying to reduce the noise that is radiating from the inlet of the engine as well as the noise that is radiating from the outlet of the engine. So one way to reduce the noise radiating from the inlet is to treat the inside of the engine with liners that absorb some of the sound before it radiates out. And then for the exhaust noise, which is a lot of it is jet noise, that's a tough problem. It is a very loud noise source, and one of the ways to alleviate that noise source has been to modify the nozzle design where you have these chevrons that protrude into the jet flow to enhance mixing, which results in less jet noise. But it's very difficult to optimize, and you have to be careful also not to affect the performance of the aircraft. But at least as an acoustician, we propose ideas that will alleviate the noise problem, and then we pass it on to our colleagues in structures and aerodynamicists, and who look at the other problems and see if there is any consequences to those noise reduction devices. One promising way to reduce aircraft noise is to shield it. And that's something that we're looking into now with a hybrid wing body configuration. It is an aircraft design where the wings are smoothly blended into the main body. So it's like a flying wing, and we call it hybrid wing body. And on those aircraft, you can place the engines on top of the airframe, and then the aircraft forebody can be used to shield the noise that is radiating from the engine inlet. And then you try to place the engine as far upstream as possible, as far forward as possible, without affecting the aircraft performance, to also get some shielding from the trailing surfaces, shielding of the jet noise. So NASA is trying to reduce the noise around the airport. That's something that is very important. So we're trying to pretty much reduce the noise level to a level where people won't really notice that the airplane is taking off or landing.
So you want to reduce it so that maybe they're not complaining as much.
Absolutely.
And
yes,
the noise
yes.
isn't bothering them.
Yes, yes. So we want to develop aircraft that have minimum impact on the environment, and that includes noise.
So Florence, in the future, people that live around airports currently may not be able to hear those aircraft taking off and landing.
Absolutely. That is NASA's goal.
Wonderful. Thank you so much,
You're
Florence.
very welcome.
As we've seen so far, NASA is really working hard to make flying greener, and there is so much going on, including cutting-edge research in alternative fuels to common-sense alternatives, like the use of automated systems to make aircraft more efficient. And new tests are being conducted that could help make radical changes with engines. Johnny Alonso headed to Seattle, Washington to meet up with a NASA engineer who's working on those tests.
When you think about making an aircraft environmentally responsible, what's the first thing you think of? Making less air pollution, right? Definitely. It's one of the major areas of study for NASA. Another area that's often overlooked is reducing noise pollution as well. For many years, there's been a real push to find ways to make aircraft environmentally responsible for the amount of air and noise pollution they put out. And thankfully, NASA and its industry partners have been working very hard at these problems.
During the late 1950s and 60s, passenger air travel changed dramatically with the ushering in of the jet age. This period of history introduced the public to large aircraft powered by turbine engines. These aircraft are able to fly much higher, faster, and farther than older piston-powered engines, making transcontinental and intercontinental travel considerably faster and easier. For example, aircraft leaving North America and crossing either ocean could now fly to their destinations non-stop, making much of the world accessible within a single day's travel for the first time. Since large jetliners could also carry more passengers, airfares also declined, so people from a greater range of social classes could also afford to travel outside of their own countries. Of course, a major drawback was that these early aircraft were loud, and they were also gas guzzlers. The gas problem became more evident during the oil crisis of the 1970s. This crisis energized many engineers to look for viable solutions to the problem. One of the solutions they found was a new type of engine called the open rotor. This type of engine was very efficient, but it was also very noisy. This engine has shown much promise, but as gas prices receded, the development of these engines stalled, while work on the more advanced turbofan engines continued.
But recently, engineers have begun looking at the open rotor again. And this time around, they think they can make it a lot less noisy and a lot more efficient. So what is an open rotor, and why is it so promising?
Well, Johnny, an open rotor has got two sets of blades that are rotating in opposite directions. And these blades are large when they would be at full scale on an aircraft. These blades are also, special blades are designed to operate at high cruise speeds, so high subsonic cruise speeds that are typical of aircraft that we fly in commercial air transport today. Now this large blade diameter, which could be 10 feet or more on a real aircraft, also means that a lot of airflow is going to be moving through the blades, being propelled by the blades, relative to a smaller amount of air that's going through the engine core. This is going to give us much higher efficiency for these types of engines, and is one of the big advantages that's so promising about the open rotor. But it's called an open rotor because there's no duct surrounding these blades, like you see on most turbofan engines on commercial air transports today. And because there's no duct with its sound-absorbing acoustic liners, it's also going to make open rotors very loud.
How do you think you can make this less noisy?
Well, it's a very difficult problem. One way is to work on the source noise, the noise that the engine itself is producing. And that can be done through like blade design, for example. Another way is we can work on how the aircraft flies. Right? So whether it's flying a little bit slower or flying away from communities, operational effects like that can have a big impact.
And before we locked in cameras, you and I were talking, and you mentioned something about mounting the engine like somewhere else on the craft. Would this help with this noise reduction?
This type of experiment is designed so that we can explore the positions and the ways in which we can integrate the engine and the airframe to make the complete aircraft system. We feel that there are ways that that can be useful to reduce the overall net noise that's radiated to the community below. This effort is part of NASA's Environmentally Responsible Aviation Project, which has as goals to reduce fuel burn, reduce emissions, and to reduce noise simultaneously. And so what that requires is efficient engines and airframes that can reduce fuel burn, fuel consumption, but we have to do it in a way which reduces noise at the same time. It's like the same as comparing today's aircraft, which are very good, to aircraft, the first jet aviation aircraft. Right? That amount of noise reduction is what we're trying to achieve in the future.
Behind you, you're working on this futuristic looking aircraft. I mean, will this work on commercial aircraft as well? Or other aircraft?
Yes, it's very relevant to other types of aircraft. Again, what we're looking at here is the effects, the aeroacoustic effects of integrating propulsion and aircraft. At NASA we call that propulsion airframe aeroacoustics. It's very relevant to any type of aircraft that you put together because you have to integrate engine and airframe to come up with the aircraft system.
What is so special about this facility?
It's the Boeing company's low-speed aeroacoustic facility. And NASA is working with Boeing on this experiment. It's an aeroacoustic wind tunnel, which means it's specially designed to be able to measure noise properly for aircraft applications. So you can see it's a large chamber that's got soundproofing material. It has a large wind tunnel, 9 feet by 12 feet. And we can put the airframe and the propulsion source here in the wind tunnel, and it's got all the right instrumentation that we need to measure sound properly. We've got it all here. And one more important aspect is that this airframe can move relative to the propulsion source, so we can investigate all those different combinations of the engine and airframe together.
I see that the guy's already taken off, so I guess you're going to be starting up a test. Russ, thank you so much for having us out, and good luck with the project.
Hey, thanks for coming.
It's my pleasure. Take care.
As we've discovered, decreasing pollution while at the same time increasing efficiency is an important goal at NASA. So you can bet in the near future, aircraft of all kinds will be much quieter and produce much less pollution. Thanks to NASA. That's it for now. For Johnny Alonso, I'm Jennifer Pulley. Catch you next time on NASA 360.
Another area that's often overlooked is the reducing of
more efficient. And new tests are being conducted that could help make radical changes today. As we've discovered, decreasing pollution and increasing efficiency is an important goal at NASA. I don't know what I'm saying. And one of the best examples of this is NASA's expeditionary something. Environmentally responsible aviation.
If we cannot keep it reduced.
Really? Another area that's actually overlooked is the right there. Another area that's often overlooked. Yeah, right.
And one of the best examples of this is NASA's. Oh my gosh!
Are you filming? Back to the smile.